Thermodynamics in Biosystem, Module 3, Energy, Segment 2, Energy Transfer. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about forms of energy. In this segment, we will discuss about energy transfer. Energy transfer by heat. Energy can cross the boundary of a closed system in two distinct forms, heat and work, as shown in the left figure. Heat is defined as the forms of energy that is transferred between two systems, or a system and its surrounding by a virtue of a temperature difference, as shown in the middle figure. Energy interaction is heat only if it takes place because of a temperature difference, which means that there cannot be any heat transfer between two systems that are at same temperature. When a body is left in a medium that is at a different temperature, energy transfer takes place between the body and the surrounding medium until thermal equilibrium is established, that is, the body and the medium reach the same temperature. The direction of energy transfer is always from the higher temperature body to the lower temperature one. Once the temperature equality is established, energy transfer stops. Energy is said to be transferred in the form of heat. The transfer of heat into a system is often referred to as heat addition, and the transfer of heat out of a system as heat rejection. Heat is energy in transition. It is recognized only as it crosses the boundary of a system, as shown in the right figure. The potato contains energy, but this energy is heat transfer only as it passes through the skin of the potato, which is the system boundary, to reach the air. Once in the surroundings, the transferred heat becomes part of the internal energy of the surroundings. Thus, in thermodynamics, the term heat simply means heat transfer. A process during which there is no heat transfer is called an adiabatic process, as shown in the left figure. The word adiabatic comes from the Greek word adiabatos, which means not to be passed. There are two ways a process can be adiabatic. Either the system is well insulated so that only a negligible amount of heat can pass through the boundary, or both the system and the surroundings are at the same temperature, and therefore there is no driving force for heat transfer. Even though there is no heat transfer during an adiabatic process, and the energy content and thus the temperature of a system can still be changed by other means, such as work. As a form of energy, heat has energy units, kilojoule being the most common one. The amount of heat transferred during the process between two states is denoted by Q12 or just Q. Heat transfer per unit mass of a system can be expressed by equation 3.9. The heat transfer rate is denoted Q, where the over dot stands for the time derivative, or per unit time, as shown in the right figure, and can be calculated using equation 3.10 and equation 3.11. Heat is transferred by three mechanisms: conduction, convection, and radiation. Conduction is the transfer of energy from the more energetic particles of a substance to the adjacent, less energetic ones as a result of interaction between particles, whereas convection is the transfer of energy between a solid surface and the adjacent fluid that is in motion, and it involves the combined effects of conduction and fluid motion. Radiation is the transfer of energy due to the emission of electromagnetic waves or photons. Energy transfer by work. Work, like heat, is an energy interaction between a system and its surroundings. Work is the energy transfer associated with the force acting through a distance. A rising piston or rotating shaft and an electric wire crossing the system boundaries are all associated with work interactions. The work done per unit mass of a system is denoted by W and can be expressed by equation 3.12. The work done per unit time is called power and is denoted as shown in the left figure. Heat and work are directional quantities, and thus the complete description of a heat or work interaction requires the specification of both the magnitude and direction. One way of doing that is to adopt a sign convention, the general accepted formal sign convention for heat and work interactions. Heat transfer to a system and work done by a system are positive, whereas heat transfer from a system and work done on a system are negative. Another way is to use the subscripts in and out to indicate direction as shown in the right figure. When the direction of a heat or work interaction is not known, we can simply assume a direction for the interaction, then solve for it. A positive result indicates the assumed direction is right. A negative result, on the other hand, indicates that the direction of the interaction is the opposite of the assumed direction. Heat and work are energy transfer mechanisms between a system and its surroundings, and there are many similarities between them. First, both are recognized at the boundaries of a system as they cross the boundaries. Thus, both heat and work are boundary phenomena. Second, system possesses energy, but heat nor work possess the energy. Third, both are associated with the process, not a state. Unlike properties, heat or work has no meaning at a state. Fourth, both are path functions. Their magnitudes depend on the path followed during a process as well as the end states. Properties, however, are point functions. They depend on the state only, and not on how a system reached that state, and they have exact differentials designated by symbol D. A small change in volume, for example, is represented by dV, and the total volume change during a process between states 1 and 2 can be expressed by equation 313. The volume change during process 1 to 2 is always the volume at state 2 minus the volume at state 1, regardless of the path followed as shown in the figure. The total work done during process 1 to 2, however, is expressed by equation 314. That is, the total work is obtained by following the process path and adding the differential amounts of work done along the way. Electrical work. Electrons crossing the system boundary do electrical work on the system. In an electric field, electrons in a wire move under the effect of electromagnetic force doing work. When n coulombs of electrical charge move through a potential difference V, the electric work done can be expressed by equation 315 and 316 as illustrated in the figure. In the next segment, we will discuss about mechanical forms of work. Until then, I am Yusuf from Institut Teknologi Bandung.